For all those who appreciate the work that we're doing here on Standing for Truth, please hit that subscribe button because we are just getting started.
One final question on genetic entropy, Dr. Carter, because I know you've written on this one, and then we'll move on to kind of another topic. But I've heard critics endlessly claim that genetic entropy cannot be true because of the existence of bacteria and mice, for example. Now, is this a misrepresentation of what genetic entropy would claim or predict? And what would be the best way to respond to that argument?
Genetic entropy was written with long-lived complex organisms in mind. So humans and elephants, we're doomed. And yet, if you look at mice, there are hundreds of subspecies of the common mouse. They have karyotypic differences. They have different chromosome counts. They're reproductively incompatible in a lot of cases, but they're the same thing. They're mice, and they were the same species. So they get isolated in a sewer line, or Delhi versus Bombay, or something like that. And they're not able to exchange genes. They have such a high reproduction rate and such a high die-off rate. I mean, if mice reproduce, every 30 days, we'll say, if that's what their generation time is, maybe 60 days, whatever it is, that means that the entire mouse population gets replaced every 30 to 60 days. That's a recipe for natural selection. With a large population, with a high die-off rate, you might be able to get selection to keep on purifying something and prevent it from going extinct. And yet, because we see all these karyotypic differences, it's not true for mice. It might be true, though, for bacteria. I wrote an article on creation.com called Genetic Entropy in Simple Organisms. And I said that bacteria are the one thing that might escape genetic entropy. Because when E. coli reproduces its chromosome, there's less than one mutation per generation. It's a few million letters. The bacterial polymerases make a mistake every billion letters. So you could have E. coli reproducing with complete fidelity, no mutations. Second, well, if that E. coli population replaces itself every 30 minutes to an hour worldwide, that means that there's an unbelievable turnover, which means that even the slight signal might be able to amplify itself over time when you have that much selection happening. So, and plus, bacteria can go dormant for a long time. And so bacteria can be continually flushed back into the environment that are the original bacteria. In fact, E. coli today, there might be an E. coli around that has the same exact chromosome as the first E. coli. Now, I doubt that, but it's possible. So genetic entropy might not apply to bacteria. It does apply to mice. It definitely applies to humans and things with very long lifespans and long generation times. It also applies to viruses. And it's like if it applies to humans and mice but not bacteria, well, the curve goes back up again. It definitely applies to viruses. We see mutation accumulation driving viral groups extinct. We see it all over the place. The influenza virus that I studied, we watched it go extinct. In fact, a creationist published that the human H1N1 virus that was circulating in the world since 1917 went extinct in 2009. The evolutionists didn't notice. That was the year the swine flu came out. The swine H1N1 was floating around, and nobody noticed the human one disappeared. So after 1918 through 2009, 90 years, actually a little less than that, it went extinct after about 13% of its genome had mutated. And it mutated randomly. We looked at the codons for the amino acids. We looked at all these different measurements. And we said, this is just random chemistry. Because C tends to spontaneously deaminate, which turns it into a U, and then the proofreading enzymes fix that as a T. So you get the C to T changes are the most common changes in the genome, and A to G is the second most common change. And what we looked at is like, this is just chemistry. But wait, whoa, chemistry? That's not allowed in evolution. Natural selection has to overcome the second law of thermodynamics, or all things are doomed to extinction. And yet, when we look at the E. coli, or the E. coli, when we looked at the H1N1 genome, all we saw was the second law of thermodynamics. We could predict what changes would happen in the future based on chemistry alone.
Incredible.
Problem for them. I was up till 2 o'clock in the morning last night, and first thing in the morning I was back at it. In fact, I worked until 7:30 or maybe 7:15. I went and took a shower and showed up here, so I'm nice and clean. But I pounded keys all day today, and I did nothing but align COVID-19 genomes.
Wow. Interesting.
I downloaded a 500 gigabyte file, which is all of the COVID-19 genomes that have been loaded to GenBank since July. I had all the ones from December to July, and I said, I got to do it again. The file is huge. I spent all day lining this up so I can analyze the changes. And the changes, I mean, you can see a direction. It's going that way.
Really?
It's not supposed to go that way. It's supposed to be natural selection does what it wants to it. Oh, no, it's going this way no matter what natural selection does.
Interesting, because I've heard that the COVID-19 virus is actually about half as fast as the average typical cold flu. Is it much slower that you've noticed? And is it
slower?
Yeah, or mutation rate, for example.
The mutation rate is hard to estimate, because for the first 5 or 6 months, there were still viruses that were identical to the first virus. They hadn't mutated yet. And other ones had 30 or 40 mutations.
Got it.
And so there's a cloud of points, and you try to draw a line through it. Well, where's that line go? But now that enough time has gone by, it's got about the same mutation rate as H1N1 and about the same mutation rate as Ebola.
Wow. Okay.
And Ebola is harder. We don't have as many sequences, and they only go back to 1976. Not like, H1N1 went back to 1918. That's a great 0 point. 1976, there's not enough time to really see a nice linear accumulation in mutations. There's too much variation and spread. And that's what we're seeing in H1N1, COVID-19. There's so much variation that we don't know, but over time, mutations will build up and build up and build up and build up, and then we can draw a line, and I can tell you exactly what the mutation rate is.
Nice. Okay. Nice. So, is it a safer type of a virus, meaning that because it mutates a little bit slower, that it would we don't have to be in much fear? Like most, cold flu season comes, every year they get a new vaccination, right? Because it's mutated so much, it doesn't resemble the original. But if COVID, what would you say to that?
I would say that the best thing that can happen to this virus is mutation.
Got it.
The evolutionists are afraid of mutation because they think that mutation leads to evolution. No, mutation leads to devolution. Mutation destroys things. Mutation weakens things. Yeah, maybe you can get some mutation that maybe the spike protein splits easier, therefore it's twice as infectious or twice as deadly. Okay, this is possibly true, but those types of mutations are incredibly rare. Most all the mutations are breaking the thing, making it weaker. That's how they treat AIDS. One of the primary way to keep the viral load in an AIDS patient down is you give them drugs that cause mutations. The viruses reproduce, they go into error catastrophe.
Right.
Remdesivir it does exactly that. It causes reproductive problems in the virus. It mutates itself to non-existence.
That's funny. It's ironic that they see it in one area, but they don't see it in the next.
Yeah.
Very good.
Yeah, but the way you just said it, though, you were hinting at, let's be afraid of mutations.
Right.
But we shouldn't be, except that it is true that a new mutation can do something bad. And that new mutation might cause this thing to spread faster or to be more deadly. We don't want that to happen. But in general, lots of mutations will just destroy it.